Hey guys, what's going on? So today we're going to be going over some more statistical mechanics. Again, if you like this kind of content, you can hit subscribe, hit that like button, and you can also go into my Patreon page. Again, my Patreon page is a little sparse right now just because I want to focus on getting content up on YouTube first. And with that being said, let's get right into the materials. So we're going to be talking, so this is, again, we're talking about Leonard Susskind in his video series on statistical mechanics. So we're now at a point where we're going to be talking about a little mathematical trick called the Stirling approximation. Leonard Susskind covers this, I believe, in I think the fourth or the fifth video in his series on statistical mechanics. So let's get into exactly what the Stirling approximation does and why it's useful, right? So we start off by taking a look at what the log of n factorial is. Now, n can be any number, right? N can be 1, 2, 3, 4. It can go up to 500, right? And the goal here for Stirling's approximation is to approximate certain quantities when we are in large numbers of n, right? So if we're taking into account large systems typically have contain a large number of states. So n could be the number of states of some system. And we want to approximate perhaps what the entropy would be of that system given the number of states, say. And so in order to do that, we need to be able to understand how we can calculate these. And one way of doing this is through Stirling's approximation. So we start off by computing the log of n. What we're going to do is we're going to derive this approximation. Now, we have the log of n factorial, right? So the log of anything multiplied by each other it sort of goes like this, right? So you have 1 times 2 times 3 times 4. What the log does is it turns that into a sum. So by turning that into a sum, we can write it like this. And then we can the approximation, right, comes into the integral, right? And because it sort of forms into the integral because we have this factor dx here, which is we're assuming this this spatial distance, right, between, you can imagine when you're integrating, we're integrating the log of some function, right? And the way we do this, again, I'm not going to draw I think this is, but we could see how we go from a discrete, I might be explaining this a little bit too difficultly, but the simple way of showing this is that we go from discrete sum, which is exact, to a continuous sum. And this is what Leonard Susskind does in his video. And by going to the continuous sum, we do that approximation. But that's the approximation because you can, if you recall from calculus, the approximations that you make like the Riemann approximation where you over approximate when you do an integral or something like that. Or you can under approximate if you do like the left-hand integration, going back all the way to calculus there. But anyways, I'm assuming we know a little bit of calculus as we go through this. This is why we go through, this is why this is an approximation, right? So when we do the log, or when we do the integral of this function, we get this, right? So this is just doing sort of rote, for me, out of rote memorization, because I've done integrals so much. You come to this point here, and then we have, so this is the log, right? So this is the log of n factorial. So to get n factorial, right? We want to raise everything to the power of e, or we put everything in the exponential, right? We put this in the exponential, we get n factorial. So we put this in the exponential, we get this right here, and it's not too difficult, I don't think, to see how we go from here to here. And then we say that e to the log of n is n, right? So e to the log of n is equal to n, and that's how we get it from there to there. So this is the approximation, right? So Leonard Susskind says that this here is essentially the approximation. We can approximate a large n, right? We can approximate large factorial n by doing this calculation, right? And so let's take a look now at some combinatorial equations. Now, Dr. Susskind doesn't really go into this that much, but I think it's kind of interesting to consider at least the permutations and combinations, especially this one, because Susskind actually does go through combinations, this combination formula, a little bit. So I think it's useful to understand this in terms of, and to understand Stirling's approximation within the context of approximating these guys, because we have these factorials in here. So before we do that, we can come to understand what exactly permutations are. Permutations, I like to think of them as, suppose you have a bin, right? And in the bin you have, say, 2 red blocks, a yellow block, and 3 green blocks, right? A permutation says basically how many, it basically tells us the number of permutations of n things taken r at a time. So if we look at this picture here, I sort of like this picture here. So if we look at this picture here, we have that we're reaching into a bin and we can get this combination. We reach into the bin again, we can get this combination, right? And so forth, and so forth. Then we have all the combinations that have yellow on them. And permutations, if we were to put labels on these guys, so 1 red and 1 green, and then we have 2 red and 2 green, and just 2 red right here. So these 1s and 2s are just labels, right? So this guy here is literally this guy here. This one here is this one here. So permutations, again, are when the order matters, right? So this is one particular state, and it's distinguishable from this state right here. Even though we have red, red, green, red, red, green, even though the color is the same, if we were to label them with a little mark or with numbers as I have here, this state is actually different than this state. Contrast that with combinations. We have the same here, but we're ignoring the numbers, right? So this here encapsulates state 1 and 3 from over here because it's red and red, right? And you can automatically see how we have less combinations than we have permutations. And this comes into the fact by when we're dividing by r factorial. That makes the denominator bigger, therefore making the number of combinations smaller. Right? This is a very important equation, and this is something that's often taught in combinatorics class or number theory class. We're not going to go too deep into it right now, but this is just, I want to give us a sense of what these factorials mean, what the Stirling approximation can do for us in the context of these real life examples. Now, I have an example, right? So how many permutations are there, given that we have 6 things, right? So we have 6 things here, 6 total things, and we choose 3 at a time, right? So 3 at a time, so we're choosing 3 at a time. We have 120 possible permutations given this configuration. Given the same configuration, we have 20, right? Count 20 combinations, right? So that is significantly smaller. Okay, and then this is something that Dr. Susskind also goes into. Also, the number of different permutations of n objects where n1 is repeated, n2 is repeated, or n1 repeated with n1 repeated items and 2 repeated items and so forth, right? So what we're doing, so we can think here, right? In these two cases, in the permutation and in the combination cases, what you're doing is you're just picking 3 out of the bin at a time. What we're doing in this case is we're taking all of them and we're lining them up. When we take these things out of a bin and we line them up. And order doesn't really matter in this case, right? Because I don't have them labeled. We can sort of think about how if order were to matter, what exactly would we have to do? But the idea here is that this is very, very important. We have two, the fact that there's 2 red, this is very important. The fact that there's 2 red in this case, 3 green and 1 yellow. In other words, we're not adding anything to our bin and then taking them all out and ordering them. What we're doing is we're just reaching into the bin and we're taking them all out. There's always going to be 2 red, there's always going to be 3 green, and there's always going to be 1 yellow. These are occupation numbers. So N1, so these are called occupation numbers. I'll write this down because this is important, an important term. Occupation numbers. And this is a state. This is another state. This is another state. And what we're going to find out, not in this video, but in a later video, is that this is, we can determine what the entropy of some given system is based off of this formula, right? So through a pure mathematical perspective, we'll be able to see that we can sort of regenerate the concept of entropy of a system, given that we have this number of potential states. And the way you calculate this again is you go through, you punch in each occupation number and you get a number out of that. Now for Stirling's approximation, for large n, right, this would be very hard to do because you have factorials get large pretty quick. So the idea is that for large n, we can approximate the number of permutations and combinations by using Stirling's approximation. So if we recall, Stirling's approximation is this. Now I'm not going to go through all this in detail. You could pause the video if you want. But the idea is, like, we just sort of plug this in to our equations, right? And we could see things are starting to cancel out, and we get these equations here as approximations for permutations and combinations. And in the next video, what we're going to do is we're actually going to apply Stirling's approximation to this guy, and we're going to get something that looks like this, right? So the occupation number, which is O, right? So this is not a 0, right? This is the occupation number. That's the occupation number. The log of the occupation number is equal to something that looks like entropy. Now, this is going to be probably going to be a Patreon link, and because this does go into some math that Leonard Susskind, I think, seems like a deviation to me a little bit in terms of what his actual point is that he's trying to get across in the lecture. So yeah, if that's something that you're interested in, I will create a derivation for this and post it on my Patreon page. And with that being said, that is what we're going to cover for today, and I will see you guys in the next one. Bye.